A few words about the mini project. All of you have a mini project, I guess, right? We've discussed this. I will skip this. Perhaps that's the classical checklist for any project. Perhaps have a look at this checklist and make sure you are able to answer all of these questions when we do the intermediate checkpoint after Easter. Right? What is your goal? What are the main issues? Which ones require detailed performance analysis? What are the load, the metrics, the factors? Are there nuisance factors? What's the solution method used by you or the paper you're studying? If it's not done by you, then those are more guidelines for what you will do. So questions 1 to 4, you should be clear on that now. If that is not yet the case, think about it, talk to me if there's a problem. That's the things I want to hear from you after Easter, before really starting the project. So that's the intermediate defense that I mentioned. Prepare a slideshow, 7 slides max. If it's 1 slide, it's fine too, but if it's 8 slides, it's not fine. So the length is up to you and depends on the nature of your project. Perhaps everything can be defined on 1. Perhaps you prefer to give more. But you should not target speaking more than 10 minutes, right? So that we have time for questions and precisions. You should all obtain a slot on Moodle. If you really have a hard exception, we will handle them out of band. If some of you cannot really make it for one of those 2 days, we'll find you a private slot. But otherwise, please use Moodle. During the public defense, which will be the last week of the semester, we have 2 weeks during which we can do that. So some of you will prefer the last week because it's the latest. Some of you will prefer the previous week because you might have other deadlines on the last week. So we will be flexible. We'll put a scheduler once the private defense is over, where you can register a slot here. And then you'll have to attend at least 2 presentations, yours and someone else's, right? Where the test that I will make with you is whether someone else, who I hope will not collude with you before, is able to understand what is your story, right? So you test it on me and the TAs of the course, but also on at least some colleagues. So those colleagues will be present to ask you questions. Right. So that's a good test to do when you do any presentation. Imagine one of your colleagues who is not working with you on the project will be attending. We will require, of course, to have all the archives. So there are 2 outputs for the project. All the files that you did, if you did a simulation program, we'd like to have them. We'll keep them in archive. We'll not make them public unless you would like to. And also the PowerPoint or the PDF of the presentation. A few things based on past experience. Do prepare to spend a lot of time reasoning about the experiments and not writing codes for the simulation, right? If you plan to spend a lot of time writing the experimental code, this is not the goal of this project, right? The goal is a bit like in Lab 1. Your job is really to think about the experimental design, the exploitation of results. So if you have to write scripts, it is scripts to automate the simulation. But if you're still debugging the simulation, the basic simulation, this is not okay. You should debug everything before Easter, before the project starts, right? It's an evaluation of an existing project. I'll say a few words about graphics. Well, the last thing, don't believe everything that's written in the literature. Of course, that seems obvious, but if you read something in a paper, it's not enough, right, to be true. It's not because it's written in one, even IEEE transaction paper, it's not necessarily true. Like any good journalist, you should check things. If it's a simple thing, you can look at the proof and see if it's doable. If the proof is very complicated or involves a sequence of other papers, you need to do a plausibility check by applying your best common sense, or what I call the differential compression method. You try to imagine why this thing is like this and try to make your own story about that. If you can't, there might be a problem either in your understanding, perhaps you don't really understand what is meant and you're using it in the wrong sense, or the thing that is written is wrong, or is wrong in the setting for which you use it. Some papers have oversimplifying things that are perhaps correct for one experiment, but they claim something that is not always correct. So not everything that is written is true. That's true in Facebook. Most of it is not true, but even in the literature, some of it is not true. Then I'll say a few words about the graphics. Graphics is an art. Some of you are very good at it, so please, if you're good at graphics, exploit that to make very good graphics. If you're not good at it, like me, then try your best to make it as reasonable as possible. Graphics are very important. They carry lots more information, but they can be misused. So when we do a graphic, first, they should be true. They should not be misleading. Second, if you can, they should be optimized to convey the maximum amount of information in as economical way as possible. Here's an example of graphic that I think is wrong, right? I just cut and pasted it from a paper. This graphic is comparing several energy provision methods for data centers, right? And they have a different heuristic to see where the energy should come. And they evaluate two metrics, the costs, the monetary cost. So if we use this method, that's the most expensive one. And the amount of brown energy. Brown energy is energy like coal and gas that has CO2 emission that you would like to avoid as possible. So we have two metrics. One is the money you pay, and two is the virtue you have. So the white is the best in terms of brown energy. The green DC is the best in terms of brown energy, but is also cheap, but less good than this one, for example. But I claim that those graphics have a problem. Would you agree with me? Yes?
The white scale is misleading because we start at 0.6. So the difference in brown energy between black and white seems huge.
Exactly. Exactly. So that's a very simple but common problem that's often used. If you ask MATLAB to do it, perhaps it will do automatically like this. Because MATLAB did its best effort to fill the space with the useful information. However, graphically, this conveys a wrong image. The image is what? The image conveyed by this is the size of the column. If you have a big column, it means big. If you have a small column, it means small. So this column is negligible, extremely small here, but in reality, as you said, the y-axis starts at 0. So they're all between 0.6 and 0.9 here. So the differences are much, much less than the impression given by this graphic here. In particular, this brown thing here is not 10 times better than the white one, right? It's from 0.65 to 1, so it's perhaps 1/3 better. Right? So that should be the correct graphic that you have, right? And then it's much less impressive, right? Which one should you use? Then you can reason about the arguments. That's not something we want to do here. It's something you might want to do in your project, but that's very first thing. If you want to be really smart, I'm not sure this is very impressive, but if you have very complex situations, perhaps it's even better to use things we have seen spider plots, so use those kind of techniques. You may even discover some other ones. In NumPy, there's a number of them, violin plots, etc. So take some time exploring the plots to make your thing more impressive. Here is one way, perhaps, to give the same information by plotting. I have a two-dimensional cost. I plot it in a two-dimensional space, and here I have my 4 points here. And we want to be as much as possible on the left and as much as possible below here. So here, perhaps it's even clearer that the best one is green DC, but it's also clear that those things are not comparable. Here, you lose in one of the dimensions here. So this is a bit harder to interpret, but once you take the time to interpret that, the conclusion is perhaps stronger with such a graphic here. So spend some time thinking about the graphic, not too much, but do also spend some time because it's part of the output of a performance evaluation. Now we move to the rest of to the following part of our module on model fitting, which is here. We have started a discussion where we try to find some hints and some reasonable methods or criterion in order to know which distribution to use. And we have seen that the very first basic things to reason about distribution is to know that they have a shape. The shape is the shape of the histogram that they give. That captures the distribution, how the thing is distributed. And that different distributions may have or not different shapes. Like all the Gaussian distributions have the same shape, but all the log normal distributions, for example, don't have the same shape. Right? And we have discussed also quantitative attributes of shapes that are the kurtosis and the skewness. Right? We will discuss now other attributes of a shape that are very frequently found in the context of big data. One of them is power laws. Power laws are any relationship that uses powers. X is equal to y to the power of something, or y is equal to x to the power of something. Now, classical terminology, Zipf and zeta. So the Zipf law, it's not a distribution, it's an observation, is based on an empirical statement that says that if we have a collection of objects that we sort by popularity, that's what Netflix does, for example, or iTunes, or any system that has a large number of customers, then we don't find at all Gaussian distributions for the popularities or exponential distributions, but we find things like, usually we find that the jth more popular object has a popularity. So popularity that can be, for example, captured by a model that uses the probability that it is chosen by a random user or by a random click, is proportional to 1 over the rank to some power for some index p. Very often p is equal to 1 or something else here. So we will see how such a thing can be found. This has been found empirically for a very large number of things that have very large number of users and large number of objects in their catalog. And that leads to PDF distribution on the set of integers that says if I have a catalog with capital N object, what's the probability that a random user will pick, or a random click will pick object J? Then the answer is it will have something of the form, it will pick it with a probability theta j, but theta j will not be anything, it will be something proportional to a power of j, where j is the popularity index. So the most popular will have something proportional to 1, the second most popular will have something proportional to 1/2, which means that the second is half the popularity of the first, and the third 1/3, etc. If we take p equals 0, for example, here. Originally it was with p equals 0, but it has found that p may vary a lot. That is related to what is called the zeta distribution, where instead of having a finite collection, we have an infinite collection, and the zeta distribution consists in saying I pick one object with a probability that is some constant divided by j to the power p plus 1. Now p has to be larger than 1. Why? Well, if we have an infinite number of objects, this is the probability of picking object j. We have to have the sum of the probabilities sum to 1. So the sum, now there's an infinite number of objects, so the sum, the infinite sum of all those things should be a converging series, right? So if it's in 1 over j, it diverges, it's infinity. So it's not a probability distribution if it's in 1 over j, but for p, for the exponent larger than 1, so for p plus 1 larger than 1, which means for p larger than 0, it is true here. That's for the discrete setting. Very often we work in the continuous setting because the math is easier, so the continuous equivalent of that, instead of having a finite number of objects, we will say we pick a feature x, which is a number. And the probability that feature x is chosen, and x is a continuous number instead of being discrete. Then we have something similar. It is some constant divided by x over p plus 1. Now, if x is larger than 1, the constant is easy to compute, because then all we need to know is to make sure the integral of this between 1 and plus infinity is equal to 1. So that gives p as a constant here. So it's a continuous approximation of zeta. If the number of objects is 1 million, then you can, without problem, replace a discrete distribution over a set of 1 million by something infinite first and continuous. The math will be much easier. So that leads us to a very important distribution when we have power laws, which is found typically when we have large collections of data sets, which is the Pareto distribution. It's very easy mathematically. It just means that the PDF is like 1 over a power of x, and x is larger than 1 here. The standard Pareto is exactly the one I said here. So it has this PDF, which is captured by this index. So it's the same thing saying here. The CDF is obtained by integrating this from 1 to x. And that gives simply this formula here. Very often when we reason about the tail of distributions, which is what those distributions are here for, they're here to capture the fact that when you have a very large number of objects, then you have a huge number of objects that are not very popular. So, which is exactly what happens on YouTube, right? When we post the video of this course or the video of your vacation on YouTube, okay, it will be watched, if you're lucky, a few thousand times. This will not be very popular compared to the very popular ones like Game of Thrones, right? That will be watched billions of times. So there are many orders of magnitude difference. This is what it captures here. Now, for some reason, my screen has been eaten up by the bar that should have disappeared. Okay, try to fix that. So when we are interested in this, where we want to have a final look at the tail, we look very often at 1 minus the CDF, which is called the complementary CDF, which is equal to the probability of being larger than something here. This is simply 1 over x to the power p. So that's a very simple thing to remember about the Pareto distribution here. The PDF and the CCDF follow a power law. Power law means simply it's a power. Here, y, the f here, is x to the power minus p. So in general, it's the definition of a power law. A power law is easy to visualize in log scale. If we take the log of the x and y, it means we have a linear relationship. So a power law means linear in log-log scale. Right? For the Pareto distribution, I mentioned the standard Pareto. What can we say about the shape of this distribution? More precisely, can we say that P is a location, a scale, or none, or both? And the correct answer is, so the majority says B, with another short minority, another minority says A, and both are wrong. It is not a location parameter because, in fact, all the Pareto distributions I've given have support in 1 plus infinity. So the same. If you vary P, you are in the same set. Location should shift in that set. Right? It is not a scale parameter either. If I change P, I don't have the same thing, but rescale, taken in different units. In fact, when I have a Pareto distribution, X should be unit-free intuitively. Because I start at 1 and I take x to the power something, so if p less than 1, it makes sense only if x has already been rescaled to become unit-free. Now, if I change by a scale parameter, it's impossible to change a power to another power simply by multiplying by a constant. Right? Otherwise, we would know that, and the math of powers, we would not. That's easy to prove. That's an analysis 101 exercise. But it is a shape parameter. So different p's give different shapes, right? Because it's easy to see that we can never equalize by a linear transformation, a power into another power. So we say the Pareto distribution, but it's like log normal. There are many Pareto distributions. Every P gives you a different shape. And we will see that it has an impact. Some P's have very different properties than other P's here. Here I'm showing on this graphic the complementary distribution function in log-log scale. So on the x-axis I have x, and on the y-axis I have the probability that my random number is larger than x. Of course, it goes to 0 as x goes to infinity. It's 1 minus a CDF. It goes to 1 on the left here, and it's a log-log scale. One of them is the log-normal distribution. One of them is a normal distribution, or is a log-normal distribution. Another one is a Pareto distribution, and one of them is a normal distribution. Which one is which? The majority says B, which is correct. Pareto follows the power law, so we should see a straight line. So A must be B. Then we have the choice. One of them should be log normal, the other one should be normal. And we know the log normal is, contrary to the name perhaps, is the exponential of a normal. Right. The log of a log normal is normal, which means it's the exponential of a normal. So a log normal distribution can take some large values. It's not like an extremely rare event. So it should decay less fast than the normal distribution. So I have the choice here. C must be the normal distribution. You see that it decays very quickly to astronomically small. So we're already here at 10 to the minus 12 for this value, whereas for the log normal distribution, we're 10 to the minus 2. So if we do a simulation, we will see some values here for the log normal distribution, but for the normal distribution, we will not. In fact, we see that going from here, from this to that value, the probability decays extremely fast, which is the property of the Gaussian distribution. It has an infinite support, but in practice, it's very hard to see values larger than a few sigmas away from the mean. So this should be Gaussian, normal, log normal, and Pareto here. So this is one of the methods we can use to choose a distribution by plotting the tail, by plotting the empirical CCDF. If you see a straight line after some point, then you can think as modeling the tail as a Pareto distribution. Another argument, or another criterion, that is also very often used in large data sets is called the hazard rate. The hazard rate is a terminology coming from reliability analysis, but it applies to any kind of distribution. The interpretation is this one. If we interpret the distribution as the distribution of a random variable x, that is positive, we can interpret x as the lifetime of a light bulb, or of this beamer, or of anything else. Then this definition of this is that we can take like this, is for very small dx is the probability, given that capital X is larger than x, that capital X will not be larger than x plus dx. So given this means at time x, the thing is still alive. Right? The lifetime is larger than x. So after x units of time, the thing is still living. And here is saying, what is the probability, given that you're alive at time x, that you will not be, your lifetime will be not less than x plus dx. That means that you will die in the next dx nanoseconds. Right? So that's the rate of death, right? Called the hazard rate. It depends on x. We can massage it and see this is the same as that, because given that capital X is less than x, this is known. So saying that x is larger than x doesn't change anything. So it's the same as the conditional probability here. And this conditional probability is approximately the PDF times dx divided by the probability of this, which is the complementary CDF. So the hazard rate is simply the PDF divided by the complementary CDF. It was defined for any distribution. And it has an interpretation if x is truly a lifetime. Usually, intuitively, we assume that if x goes to infinity, this, goes to 0. So it goes to infinity, sorry. So if you get older, you're more likely to die. I mean, if you're 128 years old, it's very likely that you will die in the coming year, right? And for each of you in the room, I hope it's much less likely. Right? So at least statistically, it is. So our lifetime as human beings has this property. We are aging because we die out of age, right? Of becoming older. And we become older, that means a lot of microscopic devices in our body have stopped functioning. A memoryless property means the death rate is independent of the age. Right? So given that you've observed that this device has been running for X unit of times, it gives you no information about when it will die. Right? Do you know a distribution that has this property? The exponential distribution. Right? So if our lifetime would be exponential, that means old and young have the same probability of continuing therefore. Surprisingly, there are distributions that have the opposite, that has vanishing hazard rate, which means that as x gets larger, this can go to 0. It's true for cancer cells, for example. That's some things, once they manage to survive, they will live forever, except if the body in which they live disappears. Of course, for living organisms, this is quite unexpected, but for distributions, this exists, and we will see some examples here. For example, I'm proposing here 3 distributions: exponential, Pareto, and normal. Which one is true? Is it true that exponential is an aging distribution, that Pareto is memoryless, and normal is fat tail, given that there is one of each? Out of these 3 distributions, there is one in each category. And the majority says F, which is correct. Let's see why. The exponential we discussed, we know that it is memoryless. We can verify it. The PDF is given by this. 1 minus the CDF is given by that. So the ratio is lambda, which is the rate of the exponential, which is more or less expected. For the Pareto distribution, the PDF is given by this. 1 minus the CDF is a power law with a smaller exponent. And the ratio of the two is P over X. So when x goes to infinity, that goes to 0. So power law means this, in fact. Power law, or is a special, particularly simple example, that means exactly what we can call fat-tailed. That means that given that something is large, given that something is larger than x, the probability that it will be even larger continues to be large. Right? So it's sometimes called as elephants, and it will produce mice and elephants. So the distribution will most of the time produce small values, mice, but once in a while it will produce an elephant. So given that something is not a mice, given that it is not small, there's a high chance that it will be very large. This is what Pareto captures. It's called fat-tailed. We'll see a variant of that in a second. But qualitatively, that's a very important feature. So one of the things to test if you have a large data set is to see whether this property holds. For the normal distribution, it's mathematically a bit trickier, but asymptotically easy. The PDF is an exponential minus a square. The CDF doesn't have a closed form. In fact, the CDF can be taken as one of the transcendental base functions, but it is known that it is asymptotically equivalent to 1 over x times the PDF here. So the ratio of the two is a constant times x, or is not equal, but is equivalent to a constant times x, so it goes to infinity, so it is aging, which is expected. If the lifetime of a light bulb or a beamer is a Gaussian with mean 3 years and standard deviation 3 months, That means that if the light bulb has lived much longer than 3 years, for example, if you have an old beamer or an old light bulb that has lived 6 years, it's very likely that it will die soon. Or it's more likely that it will die soon. This rate will tend to increase over time. So that is what we expect for distributions that have a finite support, or like the normal distribution that have a support that tends to be concentrated very strongly on around the mean. The Weibull distribution is very often used when you have data sets over which the hazard rate is easy to calculate, because the Weibull distribution, which is given by this formula, at least for the standard Weibull, it's another one, it is a generalization of the exponential. We see that if c equal 1, it is exactly the exponential. Here I'm giving the CDF, so 1 minus the CDF is simply exponential minus a power of x. That's the standard Weibull distribution. Of course, you can rescale and shift it, in which case you will have the general Weibull distribution. But as we have discussed, there's no need to give all the distributions, only one per shape. So C is a shape parameter. If C is equal to 1, we find the good old exponential distribution here. And if C becomes very large, we have something that looks more like a Gaussian, for this case here, or a very peaky Gaussian like here. And gamma is here the skewness that we have discussed already. And we see that if C is larger than 1, for all of those values, it's an aging distribution. It looks like a skewed Gaussian distribution. For C equal 1, it is memoryless. And for C less than 1, it's a bit like Pareto. It is fat-tailed here. So we have a class of distribution with only one parameter, C, that can be used to fit whatever property you find to your data set. So it's very often used in reliability analysis. Now let's go beyond to the extreme of what we have discussed of hazard rate that goes to 0. That leads to the concept of heavy tail. So heavy tail is something that's often ignored when we do machine learning, for example, because it makes the thing not really tractable, but something that is used when we do data analytics, because then we see that very often our distribution has this property. We see things that are not Gaussian and that have a very large tail. So it has been seen, for example, as soon as people start measuring things at very, very high resolution. For example, if you start measuring packets on a network by observing everything, or if you measure a power grid that's like using phasor measurement units at very high resolution, of time resolution, then you have terabytes of data gathered over months for any reasonable grid, for example. Then you start seeing that you have those heavy tail distributions. Heavy tail means two things. It means the variance is infinite, and it means also that very large values can happen. They're not outliers, they're not measurement errors, they're part of things that happen, rare things that happen. Mathematically, we say that a distribution with CDF capital F is heavy tailed if the complementary CDF decays like a power law. So it's equivalent. Equivalent means the ratio of the left-hand side and the right-hand side goes to 1. So it's only an asymptotic development. So it decays like a power law. For some index P, that must be less than 2. Why less than 2, we will discuss in a second. Because 1 minus the CDF is 1 over x to the power p, at least if we ignore the mathematical justifications, it means the PDF, which is roughly speaking the derivative, should be also of the order of the derivative of that. So it will be in p x over p plus 1 here. So if I take the variance of this, that means I compute the integral of x squared times 1 over xp plus 1. This will give a finite integral only if, this will always give an infinite integral because p is less than 2. So if this is true with p less than 2, we can show, and intuitively the reason is the convergence of integrals with power laws, that the variance is infinite. If p is less than 1, even the mean is infinite. So this is a distribution that does not have a mean. Right? It's hard to interpret, but it's at least mathematically existing. On Wikipedia, you'll find zillions of definitions of heavy tail. I'm using the one that's used in the framework of modeling computer and communication systems, which is the one that is easier. In Wikipedia, as soon as somebody opens the pages, everybody who works on that topic will also add their own thing. So at the end, sometimes you have something very, very complicated that obscures the main ideas because you want to have all the details. So some Wikipedia pages managed to resist this, some did not. So heavy tail is one of those, if I remember well, and there are a few others. Here are some examples. The Pareto distribution that we've seen, which is defined for every p, is heavy-tailed only if p is less than 2. If p is larger than 2, then it is a power law, but not heavy-tailed. The log-normal distribution is not heavy-tailed because even if we take the exponential of something that is Gaussian, the Gaussian decrease is like the exponential minus x squared, so it decreases faster than exponential. So even when taking the exponential of a normal distribution, we have something that still decays to 0, and we have seen that in the previous graph. We have seen that it decays faster than any power law here, right? We saw that any log-normal distribution will look like something that doesn't decay very fast, but sooner or later it will decay faster. It will not be a straight line here. So it will decay faster than any straight line, so it is not power law here. The Weibull distribution also, because of this exponential here, is not heavy tail. As you know, an exponential decreases faster than a power, so it will never be heavy tail. Here's one distribution that's often used. It's 1 over 1 plus x squared, and the normalizing constant is 2 pi. Here, if we take only the positive value of x. This is heavy-tailed with p equal 1, because the density is in 1 over x squared. So the CDF will be in 1 over x, or I integrate this. And this is heavy tail, which means with p equal 1, which means also it has infinite mean. Now, why do we care about that? Why do we give this weird distribution? Why p less than 2? Here is the reason. The reason is due to the central limit theorem. The central limit theorem is very important in probabilities because this is what gives, by aggregation, Gaussian distribution. That's why we see so many Gaussian distributions, a sum of n independent random variables. Whatever the distribution, as long as there is a finite variance, second moment here means variance, is approximately a normal distribution when n is large here. Right? That's the fundamental result of probabilities. That explains why the Gaussian distribution is so pervasive. We see it a lot, but not everywhere, as we will see. It doesn't hold if the random variables have infinite second moment. So if they have heavy tail such that the second moment is infinite, then the central limit doesn't hold. To illustrate this, I'm showing here a simulation. It's very hard to mathematically do all the details, and it would take us weeks and weeks, and I don't think this would be a good time investment. Instead, what I did is, like we do in physics, I did simulation, exploration by simulation. So I picked a distribution, for example here, Pareto with p equal 1, and I asked MATLAB to generate 10,000 samples. Right? I asked MATLAB, or I wrote a little code because MATLAB doesn't have a standard way of doing Pareto because it is so simple. And I asked MATLAB, here it was not MATLAB, it was R, which is better for plotting, but okay, it's very similar. and it plotted the histogram. And I used all the defaults, so we see the histogram is this. It's not because the software or the user of the software is stupid and we have only one bin. It is because there are, in fact, a few values, but that are so few that we don't see them. There's probably one value somewhere that is very large, and most values are very small. That's typical of those distributions. Most of the time they produce mice, and once in a while they produce an elephant. But the weight of an elephant is big, so the rare things might have a large importance. So if that's the case, it's important to model it correctly. So I plotted the histogram, the sample histogram of those 10,000 points. I plotted also a normal QQ plot, asking whether this is normal. Of course, this is not normal because there's a big outlier here, but still I plotted a normal QQ plot, and we see it's not a straight line, but it's something that is very strong curvature. I also plotted 1 minus the CDF in log-log scale. Here we see that the theoretical CDF is a power law because it's Pareto. And the true CDF, which is of course random, I compute how many times. So on the here, this means on the y-axis means how many times, or divided by 10,000, I saw a value larger than this here. So we see a straight line when there are many data points, and at the ends, when there are few data points, of course, there is less statistical smoothing. So, but it's a reasonable straight line here. Okay, those are the three diagrams I do for every distribution: QQ plot, histogram, and CCDF in log-log scale. So this is what I showed here on the left here. Then I did an aggregation, or an average, which is the same, of 1,000 samples. That means I did 1,000 times this, so which gives me 10 million data points. But I don't draw 10 million data points. I first draw 10,000 points. I take the average. I get only one value, the average of those 10 data points, 10,000 points. And I do this average 1,000 times independently. So I have an image of the aggregation of 1,000 random variables that would have the Pareto distribution. Instead of doing the math and computing the PDF of the aggregate with Fourier transform or whatever, I just do it the physics way by simulation. So I show the same diagrams: the histogram, the CCDF in log-log scale, and the Gaussian distribution, and the QQ plot here. We see not much difference in the first two diagrams, and here we see it's a bit less a straight line, but it's a straight line at the end here. This is for Pareto p equal 1. Then I did it for 4 different other Pareto distributions. Remember that for every p, Pareto is a different shape, different distribution. So I did it for p equal 1.5, p equal 2, p equal 2.5, and p equal 3. What do you see? Yes?
P grows, Pareto tends to behave as the normal solution.
When P grows, Pareto, or the aggregation of Pareto, starts looking like a normal distribution. This is correct, yes. Another observation?
Same.
Was the same. Exactly, so that's the first observation. We can see that when P was equal to 1 and we aggregate at least 1,000 times, it doesn't look at all like a Gaussian distribution. In fact, it continues to have a power law in the tail here. But if we aggregate when P equals 3, we have something that here, if we look at the QQ plot, is reasonably Gaussian. And the histogram starts really looking like a bell-shaped histogram. There are not enough data points here to make a scientific statement, but what we can say in reality is that the breaking point is P equal 2. So when P is equal to 2 or larger, the aggregation of those things will give a normal distribution. Why is that? Well, that's the central limit theorem. central limit theorem says if I take the average of 1000x, of 10,000x, so here I did the average of 10,000 things that are independently drawn from a given distribution, this is approximately Gaussian. If the distribution has a finite variance. And for p equal to, or p larger than 2, let's say, p2 is just the boundary case. If p is larger than 2, then there is a finite variance, and therefore we should have convergence to the Gaussian distribution. So one average is distributed like the Gaussian distribution. To verify that, I do the average 1,000 times. And so what we see here is the central limit theorem. What we see there, when p is larger than 2, is something a bit different. There is convergence to a distribution, but not to the normal distribution here. And the central limit theorem, the most general version, is this one, at least for heavy-tailed distribution. If we sum n random variables that come from the same distribution, if it's not heavy-tailed, it will, or if it has a finite variance, it will converge to a normal distribution. Otherwise, if it is heavy-tailed, it is converging to something else, which is called a stable distribution, that keeps the heavy-tailed property. So here, when p equal 1, that thing here is mathematically true. So the slope here, so it's only asymptotically, so it's not, for the Pareto, it's true everywhere exactly. The 1 minus CDF is equal to 1 over xp. Here, it's approximately equal to 1 over xp. The ratio between 1 minus CDF and 1 over and xp tends to some constant here. So it has a power law in the tail with the same exponent here. Whereas when p is larger than 2, there is a power law in the tail here, but this power law in the tail disappears. So there is a transition at p equal 2. When p equal 2, there is a transition from keeping the heavy-tailedness to keeping the power law in the heavy tail to no. So being power law in the heavy tail, having a power law in the tail, is something that has a practically different implication when the slope of the power law, when p, the exponent, is less than 2 or larger than 2. It's one of the strange mathematical things here. The stable distribution is the thing that it converges to. What are the stable distribution? Where it's the name. It's not a distribution that is stable. It's a proper noun. A stable distribution is a family of distributions that has two shape parameters, p and beta. So for every value of p is the power law exponent. There is one stable distribution that has also a skewness parameter, beta, something that defines how slanted it is. So more precisely, for every p, for every power law exponent, there is one standard stable distribution. And for beta, between minus 1 and 1, it dictates whether it's slanted to the right or to the left here. Why don't I give more details about it? Well, because there's no closed form for the PDF or for the CDF. So for the normal distribution, there's no closed form for the CDF, but there is one for the PDF, at least if we admit that exponential is part of a catalog of standard functions. There's no easy computation of CDF or inverse CDF, so they are ugly to work with. The only thing that's easy is the Fourier transform. The Fourier transform is null. So if you work in the Fourier domain, you can do things, but then you need to numerically invert anything you do to come back to CDF or PDF. In practice, very often in our field, we don't use them. We have to know they exist, but very often we replace them by a mixture with a Pareto tail. What is a mixture? Well, a mixture consists in saying, look at this distribution here. You know it's not Pareto, it's not a straight line, but it looks like something that could be normal or log normal, followed by Pareto. If I break the x-axis into two domains, I could fit it to two different things. Where I could keep the major tail property, which is the tail exponent, the power law of the tail, by modeling it as Pareto for the tail only. What do we do with, how do we fit things that are mixtures? Well, this is the topic we will see after the break.